Now we will move on to the NOR gate. A NOR gate is defined as a combination of OR gate followed by a NOT gate, and its output or the response is true only if all its input are false. We previously looked at the OR gate. We have input A and B, and it is now followed by a NOT gate, which gives us A plus B and inverted. And the simplified symbol is given here, and the chip can be identified as 7402 package. Also, we have 1, 2, 3, and 4 NOR gate inside this 7402 IC. And this is nothing but the physical component in which you can use in your printed circuit board. And it is also vital for you to know the pin which correspond to the input and the output. Example, we have A1, B1, which gives out Q1. And in this case, we have Q2, which is output 2, which correspond to input A2 and input B2, and so on. To compute, previously we look at the OR gate with the truth table. So the output of the OR gate, you can take the inverted of the output of the OR gate to produce the NOR gate. Now let us look at the circuit configuration using a transistor NOR gate. Now let us draw the transistor equivalent circuit. We have input A to one NPN transistor, and we have input B connected to the second NPN transistor. And this is the VCC. So for the OR gate, previously we connect from the emitter of the transistor, and we said that for the NOT case, when we are to invert the signal, we normally connect from the collector. Now this output becomes A plus B bar, which is also described as the B out. Now we can look at the switch equivalent circuit for this NOR gate, and we can have the input V in to a light bulb connected to the ground, and we can have switch 1 and switch 2, which is also connected to the ground. So we have switch A and switch B. Now we will look at the truth table. When we talk about the combination, we have 2 to the 2 input, we have 4 combination. Therefore we have A, B, and we have A plus B bar. So we can draw with respect to the 4 combination. We can have 0, 0, 0, 1, 1, 0, and 1, 1. And from this truth table, we can see from the OR gate, 0, 0 will give us 0. And if we invert the 0, it will now give us 1. And 0 and 1 for this OR gate will give us 1. And when we invert the 1, we get 0. Similar for this one, we have 1, 0. We have the output of the OR gate, which is 1. When we invert, it will give 0. And similarly, 1 and 1 will give the output 1. When we invert, will give the output 0. And this is the NOT portion of the OR gate. So both of them combined is called a NOR gate. Therefore, from the definition, we can see the output is true only if all its input are false. So we can see when all of its input are false, when A and B are false or low, the output will be high. Else all of them will be low or false, the output. Now we can explain what really happens in the transistor and switch equivalent circuit. For the first combination, when we apply 0 volts at both the input, what will happen? No current will flow in this direction and no current will flow in this direction. All the current will flow to the output. Now we have the output is equivalent to VCC or the 5 volts, and it has a logic state of 1, and we can verify from this truth table. When you look at the switch equivalent circuit, when the switch is open and open, that means no current will pass through the ground. All the current will flow through the lamp. Now we can say the lamp is on. Let's look at the second combination. For the second combination, we have input A, 0 volts, and input B, we have positive 5 volts. So what will happen? Now all the current will flow through this path towards the ground. So the output will be 0 volts, which is equivalent to a binary state of 0, and we can prove it from the truth table. Therefore, when switch B is closed, the current will flow through switch B and the lamp will switch off. No current will pass through the load. The third combination, we have 5 volts at input A and 0 volts at input B. Now all the current will pass through this transistor and towards the ground. No current will flow to the voltage out to drive the load. Therefore, the output will be low and having a binary state of 0, and also can be proved from the truth table. Similarly, we will now have current flow through switch A. No current will pass through the lamp. Now the lamp is off. And finally, the last state, both the switch is on, so we can say both are closed. Therefore, current will share equally to the switch towards the ground, and no current will pass through the lamp. Also, the lamp will be off. Similarly, apply positive 5 volts to both the input. Now the current will flow to the ground in this transistor and in this transistor. So the output will be 0 volts, which is equivalent to a binary state of 0. I believe with this simple explanation, you can be able to fully understand the NOR gate. And I will give you one simple example in a real application in which you can apply NOR gate to control a circuit with a sensor. So let us look at this example. We can say application of a NOR gate. Imagine you have a house and you have a light dependent resistor connected outside, and you have another light dependent resistor too connected inside the house. And outside the house you have the spotlight. Let's say you have a spotlight. The condition is that when the light dependent resistor 1 and 2, when both of them goes low, we want the spotlight to shine, maybe in case of a security purpose. Now we can design a circuit that will help us understand how this application of a NOR gate will work. And when light decreases, the resistance will increase. Now, by understanding the operation of the LDR, we can now formulate the circuit. We can simply have the NOR gate, which simply connected to the spotlight. This is now our spotlight. And the input, how can we design the input? It is very crucial for us to design the input of the NOR gate with respect to the input condition of the light dependent resistor. Imagine you have the circuit connected like this and to the ground. And for the input, we have the LDR1 and we have the LDR2, and we can have R1 and R2. And now this one is connected to the VCC. This region represents the input, and it is important for you to understand that the input determination of whether it is high or low is based on the input to the particular NOR gate and not the VCC. VCC is not the real input. The real input to the gate is connected here, and this is the output of the NOR gate. Now we can look at the daytime. During the day, there will be light on the phase LDR. That means this resistance will be less. So there will be current flowing through input A, and this can be input B. During the day, we can say this will have a low resistance. Whether there is light inside the room or not, it does not matter. And we can say for the LDR2, for example, if inside the room is dark, now we will have the resistance which is high in this case. So even though there are light in the LDR1, it will now allow current to pass through the input A. And if it is high, then there won't be any flow of current in input B. Now we can have the input A, which is 1 and 0. When we have 1 and 0, the output of the OR gate will be 1. When we invert the signal, it will be low. Therefore, the spotlight will be off. And in a case where there are light appears in the LDR1, which will now have low resistance, and it will conduct current to input A. And if there is light inside the house for LDR2, then the LDR2 will have a low resistance and it will also conduct. So we will have both input to the NOR gate will be 1, and we know that the output will be inverted. When we have both input 1, the OR gate will be 1 and inverted, it will still gives us off. Now finally, in the case where in the night there won't be any light to LDR1. Now we will say the resistance is high in this case, so no current is allowed to pass through, and we can have 0 volts at input A. And imagine if we have the light inside the house, that means someone is still awake. Then what will happen? The resistance will be low, and we will have 5 volts appear at the input B, which can represent the logic state 1. Now we have 0 and 1. For the AND gate, it will be 1, and inverted will give us 0. So still the spotlight will be off. So the spotlight will be on only when there is no light at LDR1 and people in the house, they go to sleep. Now they can switch off all the light. That means inside the house is dark and outside the house is also dark. In that case, we now will have high resistance in LDR1 and also high resistance in LDR2. Now what will happen? No current will pass through. Therefore, input A, we will have 0 volts, and input B, we will also have 0 volts. Now 0 and 0, The output of the OR gate will be 0. When we invert, it will be 1. Now we will have the spotlight on. So the spotlight works in such a way where both the room or inside the house and outside the house is dark. Now the spotlight will go on. If one of these conditions is not true or both of these conditions is not true, then the spotlight will be off. We can see that when there is light, we can say the condition is true. When the dark, we say the condition is false. So when the condition is false, the output will be on or it will be true. So this is one good example in which can help you to understand what is a NOR gate. If you like our video, you can kindly click the subscribe button, and you can also click the notification bell. Every time we post our new video, you can be notified of the video. And also you can share with your friends so they can be able to learn what is the basic logic gates.